Very well. So we're going to talk about the graphs of trig functions. The very first graph that we're going to discuss is y equals to sine of x. Well, as you remember, sine of x is a function that continues on both sides. So it goes to the left and also to the right, and it continues the same behavior as it goes along. Well, we learned that the period of sine function is 2 pi. What's the meaning of that? It means that this part of the graph repeats itself on both sides. The period is 2 pi. After 2 pi, 0 to 2 pi, the graph repeats itself. So next, you have 2 pi to 4 pi. The graph stops and starts the same behavior after 4 pi. 4 pi to 6 pi, 6 pi to 8 pi, and so on. Well, you're going to see the exact same behavior on the left-hand side as well. Negative 2 pi to 0. Your graph is going to have the exact same shape. As you can see, the range of the function is sandwiched between -1 and 1. The domain is between negative infinity to positive infinity, and the range is -1 to 1. The second function is cosine function. Well, the behavior of cosine is like this. When you plug in 0 for cosine, cosine of 0 is equal to 1. So the starting point for cosine is at this point. Well, it starts going down. At pi over 2, your cosine is equal to 0. Then at pi, it's -1. Then it goes up. At 3 pi over 2, the outcome is 0. And then at 2 pi, cosine takes the maximum value, which is 1 again. So your cosine takes its maximum value at 0, which is 1, and at 2 pi, which is 1 again. It takes its minimum value, which is -1 at pi. Well, okay. As you can see, the graph continues from both sides, to the left and to the right. So the domain of the function, the domain is related to x values. You can plug in any x value into this cosine function. All acceptable numbers are on the horizontal axis. So that's why the domain of the function is -infinity to +infinity. Well, what about the range of the function? As you can see, this function doesn't go up, it doesn't go down. It oscillates between -1 and 1. So remember that the range of the function are related to y values. So if you look at the shadow of the graph on y-axis, it's going to be between -1 and 1. So we write range, all y values, such that y is bounded between -1 and 1. Note that -1 and 1 are also included. As you can see, the period of cosine function is also 2 pi. The graph has a behavior between 0 and 2 pi, and it keeps repeating the same behavior to the right and also to the left. So the period of sine and cosine are both the same. Very well. So let's take a look at these in more detail. So your sine function at 0 has y value which is 0. Then at pi over 2, if you plug in pi over 2 into the sine function, the y value is 1. 1 is the maximum value of your function. So if the question says, hey, what is the maximum value of sine function? You're going to say, hey, the maximum value is equal to 1. And if the question says, at which number, at which x value the function takes its maximum, you're going to say, hey, when x is pi over 2, my maximum value is 1. Well, as you can see, you have a decreasing behavior for your function, decreasing behavior for the function, and then the graph hits x-axis at pi. Well, it keeps decreasing, and then it takes on its minimum value, which is -1. So if the question says, hey, what is the minimum value of sine function? You're going to say, hey, the minimum value of sine function is -1, and it happens at 3 pi over 2. When x is 3 pi over 2, my y value is -1. Well, the graph starts increasing and it hits x-axis at 2 pi. So sine of 2 pi, we all know, is equal to 0. This is a full period, full cycle for your sine function. As you can see, it hits x-axis at 1, 2, 3 points on full period. But as you can see, the graph continues from all sides. So it has infinitely many x-intercepts. On one full period, complete cycle, you have 3 x-intercepts. But if the question says, hey, how many x-intercepts sine function has? How many zeros sine function has? You're going to say infinitely many, because the graph continues its behavior in all sides. But if the question says, hey, on one complete or full period, how many zeros sine has? You're going to answer 1, 2, and 3 zeros. What are those zeros? One happens at 0, one happens at pi, the other one happens at 2 pi. Take a look at your cosine function. We know that cosine of 0 is equal to 1. So cosine takes its maximum value, which is 1, when x is 0. Well, it starts falling. It hits x-axis at pi over 2, and then it keeps decreasing. It reaches to its minimum value, which is -1 at pi. Well, when it took its minimum value, it starts rising. It hits x-axis at 3 pi over 2, and then it goes up and stop at 2 pi, and it takes on its maximum value. Lost the connection, everyone. So your cosine takes on its maximum value at 2 pi. Very well. So this is the behavior of cosine on one full period or full cycle. As you can see, on one full period or full cycle, you have two zeros, two x-intercepts. One happens at pi over 2, the other one happens at 3 pi over 2. So if the question says, hey, how many zeros cosine has on one full period or full cycle, you're going to say, hey, it has two zeros. What are those zeros? Pi over 2 and 3 pi over 2. But note that if the question says, hey, how many zeros a cosine has, you're going to say, hey, it has infinitely many zeros. The graph hits x-axis at infinitely many values because the graph continues on all sides. Let us just graph Desmos. Sine of x. Well, okay. This is the graph of sine of x. This is the actual graph on its domain. The domain negative infinity to positive infinity. It keeps going. So how many x-intercepts do we have? How many zeros do we have? These are all zeros of the sine function. How many can be counted? There are infinitely many. There are a lot of x-intercepts. There are a lot of zeros. All of these are zeros, x-intercepts.
So if you want to find the zeros of, like, say you have 10.
Very well. So let us take a look at the definition of amplitude and period. In general, we can define a sine and cosine function using transformations that you learned in previous pre-calculus class. In the rest of this section, you'll study the graphic effect of each of the constants a and b, c and d in equations of the form y equals to. Well, we usually have a constant like d plus, we multiply the sine function by a, and instead of just having x as the variable, we're going to use a general form bx minus c. This is our sine function in its general form. Well, we're going to have the exact same definition for cosine function. These are all coming from transformations that you learned before. Each multiplication, addition, subtraction has a different impact on the sine and cosine function. The constant factor a in y equals to a sine x acts as scaling factor. A vertical stretch or vertical shrink of the basic sine curve. Note that if the absolute value of a is larger than 1, then the basic sine curve is stretched. And when the absolute value of a is less than 1, the basic sine curve is shrunk. Okay. The result is that the graph of y equals to a times sine x ranges between negative a to a. Instead of negative 1 to 1, you're going to change the range between negative a to a. The absolute value of a is called the amplitude of the function. So the range of the function y equals to a sine x when a is larger than 0 is negative a to a. Okay, suppose we make some changes to sine function. This is my sine of x. We already know the behavior of sine. Now I'm going to have 2 times sine of x. Well, this is my sine function. The red graph represents the sine. The blue graph represents 2 times sine. What if I multiply that by 3? 3 sine x. Well, as you can see, your graph has changed in its range. The range of sine is between -1 and 1. This is the range of sine. The range of 2 times sine, the blue function, is between -2 to 2. The range of green function, which is 3 times sine, is between -3 to 3. Guys, note that there is no change in the period or in the domain of the functions. We are just changing the y values by multiplying this by different numbers. You might say, hey, can I multiply this by a fraction? Yes, of course. 1/2 sine x, it's going to give you this purple function, which is getting closer and closer to x-axis. Well, as you can see, the range of this function, purple function, is between -1/2 and 1/2. The range is getting smaller. Y values are getting smaller, but the period, they're all the same, 2 pi. Domain -infinity to +infinity. There is no change in the period. There is no change in the domain. The only change that we see is on y-axis or the range of the function. Okay, now let's just try to see what if I change my sign. Now I have sine of x plus, suppose I'm going to add something like pi. Wow, interesting. Take a look at your graph. The red one is the sine function. Now that I changed my x value, I have sine of x plus pi. So I'm changing my x values. If I plug in 0 for x, then I end up with sine of pi, which is 0. If I plug in, for example, pi here, I get sine of 2 pi, which is 0 again, as you can see here, pi and 0. If I plug in 2 pi, I get 0 again. What if I plug in something like pi over 2? Sine of pi over 2 plus pi is 3 pi over 2. Sine of 3 pi over 2 is going to be -1. So instead of having a maximum value, I end up with a minimum value. This is the behavior of sine of x plus pi. What if I change it this way? Sine of x plus pi over 2. Let's see, what do we have here? Oh my God, take a look at the graph. This is now the black graph, sine of pi plus 2. See, if you change your x value, x variable, you're going to see different shifts in the graph of your function. If you plug in 0 for your x, then you're going to have sine of pi over 2, which is 1. At 0, you have 1. At 0, your sine of x plus pi over 2 takes its maximum value. Take a look at your original sine. The original sine passes through the origin, but now that I changed the function, I added a constant to x, I see changes in the graph of the function. I see some shifts to the left-hand side. Well, now what if we just make more changes? Now, suppose I'm just multiplying my sine of x and change the x to 2x. Wow, take a look at this. Here I have my sine function, which is red. Now I have a blue function, which behaves differently. You actually see the change in the period of the function. This blue function doesn't have the same period as the sine function. Very well. My sine function has period 2 pi. This is the red function. And here, the blue function sine of 2x, it has period which is pi. It repeats itself after each pi. Take a look at this. What if I have sine of 3x? Oh, wow. There is more changes. They're getting closer and closer to the 0. As you can see, here you're getting smaller period. Smaller period. If I multiply that by 4, sine of 4x. Ooh, wow. Now I expect you to ask, what if I change these to a half, to a third? What changes do we see here? So suppose you have 1 divided by 2x. Well, take a look at this. If I multiply x by a half, by smaller numbers, the behavior, it's absolutely different. The red function is your sine function. Here, the blue function is sine of a half x, which has larger period. The period of the blue function is 4 pi. The period of sine function is 2 pi. See the difference between them? So if you change your x value, multiply by that by different numbers, you're going to see changes in the period of the function. So sine of 2x and sine of a half x and sine of x itself. So the green one is sine of 2x with smaller period, and sine of a half x with larger period. Very well. So when we have y equals to a times sine of bx, or y equals to a times cosine of bx, the period is going to be 2 pi divided by b. So the number that is multiplied by b is going to be on the denominator. So b times x, the number that is multiplied by x, which is b, is going to be on the denominator. So if you change your sine function, y equals to a sine of bx, the only number affecting your period is b, which is multiplied by x, and your period is 2 pi over b. As we saw, sine of a half x, let's take a look at our Desmos. Here we have sine of a half x. Here, the period is 4 pi. 2 pi divided by a half is 4 pi. So sine of a half x, our b is a half, and the period is 2 pi divided by b. And then, as you can see, it is going to be 4 pi. Okay, so let's talk about the translation of sine and cosine. The constant c in the general equations, y equals to a times sine of bx minus c, and y equals to a times cosine of bx minus c, creates horizontal translations or shifts of the basic sine and cosine curves. Comparing y equals to a sine of bx with y equals to a sine of bx minus c, you find that the graph of y equals to a times sine of bx minus c completes one cycle from bx minus c equal to 0 to bx minus c equals to 2 pi. So by solving x, we can actually find the end points for our horizontal change. So we set x between c divided by b. Where did it come from? If you move c to the other side of the equation, you get bx equals to c divided by b. X is c over b. The same for the second equation. By adding c to both sides, we get bx equals to 2 pi plus c dividing by b. X is c over b plus 2 pi over b. The number c over b is called the phase shift. Let us take a look at some graphs to feel more comfortable. Very well. So let us analyze sine of 2x and then sine of 2x plus pi over 2, for example. Okay, let us take a look at the graphs a little bit more closely. This is my sine of x. This is my general function. It is well behaved. Well, the period is between 0 to pi for the sine function. For sine of 2x, remember that here you have 2 pi divided by 2 because your b is 2. So 2 and 2 cancel out. We expect the period to be just pi. We can check the graph. This is our blue graph. And then here you see the period is exactly pi. This is what we expected. What about this guy here? We have 2x plus pi, or we can do the subtraction, 2x minus pi. Well, to find the period for this function, we're going to set 2 pi minus 2x minus pi over 2 equal to 0, and 2x minus pi over 2 equals to 2 pi. So let us take a look at this together and write everything down. Okay, let me share this with you. Erase the board. Move this guy up a little bit. I want you to check the graph as well. So, very well. So for sine of 2x plus or minus pi over 2, let us write down minus pi over 2 to follow the formula. To find the period, we have to do two things. We need to set the quantity inside parentheses equal to 0, 2x minus pi over 2 equal to 0, and also set 2x minus pi over 2 equals to 2 pi and solve these two equations. Okay. So one by one, we're solving these two equations to find the lower limit and upper limit for x. So for this guy, I'm going to add pi over 2 to both sides and then divide everything by 2. Pi over 2. So as you can see, negative pi over 2, they cancel out each other. So what are we going to have? We're going to have 2x equals to pi over 2. Well, now divide everything by 2 to isolate your x. You're going to have x equals to pi over 4. This is your lower limit. Pi over 4. Here we go. So this is my lower limit. The same for this equation. First, we add pi over 2 to both sides to get rid of the constant. Pi over 2 plus pi over 2. Very well. So we can cancel out pi over 2, negative pi over 2. Well, what are we going to have? We're going to have 2x equals to 5 pi over 2. 5 pi over 2. Well, now to isolate x, sorry, on the other side, it's not pi, it is x. So my x is equal to 5 pi over 4. Nice and easy. Amazing. So the period is between pi over 4 and 5 pi over 4.